Okay, so I will talk about deep packet inspection. Deep packet inspection is the process of classifying packet according to the packet payload. It's done against known set of patterns, string or regular expression. For example, here you have a firewall. The firewall has a rule. If you find evil in the payload, you should stop the packet. And here is the packet. The packet comes. The firewall performs the deep packet inspection and stop the packet. It's a very common task. You can see it in IDS. This is an example for Snort. This is a regular expression. And you see here the star, which means to repeat these characters 0 or more times. And this is a cross-site information disclosure rule. Okay? And this is ClaimEV. ClaimEV is antivirus, an open source antivirus. Here it's a string that identifies worm. And deep packet inspection is a common task in many of the middle box today. Middle box are all the devices in the network which are not switches and router. There are many middle box today in network, in some networks, more than the switches and router. And this is because the network become more and more sophisticated with time. You need to do decision about performance, monitor, and security. For those, you need to look into the payload of the packet. So let's go over on a list of a middle box that has used DPI. You have intrusion detection, antivirus, firewall, network analytic, copyright enforcement, load balance, traffic shaper, lawful inspection, leakage preference system, and more. Okay? And now I want to talk a little bit about the market. It's not a typo, deep packet inspection. I want to understand what is the market. So 66% of all the vendor equipment define DPI as a must-have technology today. And DPI market, the estimate is 3 years ago around $500 million. And they estimated to grow that in 3 years it will reach almost 4. And this is because the network become more and more sophisticated, and for that you need a deep packet inspection. Okay, so why am I talking about deep packet inspection? Because it's a complicated challenge. DPI engine is considered to be a system bottleneck in many of today's middle box. 30% up to 80% of the time spent in the middle box is in the DPI engine. We repeated simulation in our lab with middle box like Snort and ClaimEV. There are hundreds of papers over recent years dealing with scalability, throughput, latency, power, resilience, update, compression. What is the agenda of the talk? I decided today to give an overview on the subject, to talk about the challenges and opportunities designing a deep packet inspection. This is a summary of a 5-year study. 5 years ago, me and Professor David Chai, founded a lab, Deepness Lab. You can see the acronym, thanks to Yotam, our student. And we received a ERC, generous ERC starting grant, and then 2 magnet. Here are some of us and some of the students. So my goal in this talk is to give you overview. I will discuss a little bit about our works. I wouldn't go into the details. Okay? This is what I choose today. So, what are the major challenges? It's very surprising that I'm talking about deep packet inspection because it's a well-studied problem in computer science. You know, find regular expression in data, finding pattern in data, string in data. This is the classical problems in computer science. But the solution, the theoretical solution, are not sufficient to the current demands. Okay? And let's understand why. I decided to concentrate on the 3. I think they are very important one. First is the scalability. You need to deal with rate, which is the 10 or even 100 gigabit per second. This is the rate middle box today works. Memory. You need to handle thousands of patterns. This is the set of patterns of middle box today. If you look at Snort, ClaimEV. The traffic becoming more and more sophisticated. I will concentrate on the fact that most of the traffic today is compressed. Okay. Also, you have the question of security of the DPI engine itself. Because the DPI is such an important component in security tools, you must have the DPI itself to be secure. Otherwise, the attacker will first attack the DPI engine part in the middle box, for example, in DDoS attack. And after it, he will get to the network. So we'll talk a little bit about it. I will talk not only on challenges, but also on opportunities. Deep packet inspection, I think, will change due to the two big revolutions today of software-defined network and network function virtualization. By the way, the fact that the importance of deep packet inspection will be more and more in the coming year, it's because also of the SDN, because SDN give you ability to control flows smartly, and for that you need to understand how to categorize flows, and to categorize them cleverly, you need to look into the packet payload. So this is more or less the agenda of today. Okay? So first challenge, I want to explain why you have a scalability problem. So the basic solution you have for finding regular expression, here you have example of regular expression, it's NFA and DFA. NFA, you have a finite automata where in each characters you move to one or several active states. Hence, the problem of NFA that if you look on memory and time, the time that NFA requires is huge, because in reality you have several active states. So you need to process several active space parallel. On the other hand, you have DFA, deterministic finite automata. There you move to the only to one next step, okay? But the problem, you can even see it here, it's that you have more state. In the worst case, potentially you have 2 in the power of the number of states of the NFA. Today, for middle box, it's impractical to build DFA. Okay? So they cannot build DFA, it's too huge. There is a big memory blow up. So what solution is done today? The current solution in most of the middle box, for example in Snort, is to take two-phase approach. In the first phase, they take from the regular expression all the strings that appear in the regular expression. Then they do string matching over all the strings that appear in the combined set of the regular expression. And then, if they find that in this traffic all the relevant string of some regular expression is matched, then they run a single DFA, okay? Only of the corresponding DFA of the regular expression. And you have several regular expressions that's matched. They will run again and again a single DFA for the corresponding regular expression. So you can understand it takes time, okay? But in most cases, it works, okay? In the average, it works. Other academic solution is to try to do some hybrid approach between DFA and NFA. There are a lot of work of how to do it smartly. Okay? Okay, and what about string matching? It should be easier. So the common algorithm of string matching is all-thoracic, which builds the DFA. Usually they store a full table DFA, which means they have an array of every state and every alphabet. And then for a given state and a given character, they move in one memory read to the next state. The problem is with today's number of patterns, the memory requirement is a little bit huge. But the problem is not only the space, but also the fact that with this memory requirement, you are running not on fast memory, but on slow memory. It cannot fit to fast SRAM memory. So many efforts to solve also this bottleneck. We had some work also on this subject. this is the first challenge. The second challenge is dealing with compressed traffic. And you need to understand that 60% of all the HTTP traffic today is compressed. And if you look on the top 1,000 sites, the percentage is even higher, 84%. And they use compressed traffic because they want to reduce the bandwidth. And data compression is done by adding reference pointer to repeated data. Usually it's gzip and then Huffman. Let's see an example. We have here a data for a page, HTML page from Yahoo. You have here a reference. The reference mean go back and copy from back 26 bytes, copy exact 6 bytes. Go back 26 bytes, copy 6 bytes. This is how it's done. And the problem is that current solution tools do not deal today with compressed traffic to the high challenges in time and space. Which if you think about it, it's a little bit frightening because they ignore a huge amount of the traffic due to the following problem. So let's understand the problem. The problem with compressed traffic from the time aspect is that you need to decompress period to the pattern matching. And this is because HTTP compression, gzip, is an adaptive compression. It means that the same string will be encoded differently depending on its location in the text. Okay? So you need to do decompression and then pattern matching. And if I just talk and say that pattern matching is a pain, they think, okay, if I need also to do decompression, it's a huge pain. So I ignore it. Okay? In a work we did, we tried to accelerate deep packet inspection and very successfully. The idea is that compression is done by compressing repeated sequence of bytes. So the idea is to store information about the pattern matching result. Then there's no need to fully perform again pattern matching or repeating sequence, which were already scanned. We receive 2 up to 3 time reduction. So it's a powerful idea. And the observation is that when you decompress and doing pattern matching, in fact, you are much faster than doing pattern matching because you can use the information from the compression. Okay? The basic idea was 6 years ago was on string matching, and now in the coming Infocom we have a paper how to do it with regular expression, NFA and DFA. The idea was so powerful, so we thought how to use it also on uncompressed traffic. And what we thought is how to accelerate by identifying repetition in the uncompressed traffic. In uncompressed traffic, there are many repetitions because most of the big site compress the traffic because they know it's useful. And why there are repetitions? Because you have repetition of entire files, like image, and also you have repetition on part of the files, like HTML tags and JavaScript. So what the DPI engine does, it keeps scanning again and again the same thing, and receive again and again the same result. So in the coming Infocom, we will have a paper about how to accelerate deep packet inspection in uncompressed traffic. And the idea is to identify frequent repeated data fastly, perform DPI on the data once and remember the result. And then when encountering repetition, we recover the state without rescanning. Okay? This is from the time perspective. From the space perspective, okay, in compressed traffic, there is also a huge challenge. If you ask me, I think this is the main problem why most of the company ignore compressed traffic. The problem is that you need to store the last 32 kilobytes per session. And this because the repetition can be to any place in the last 32 kilobytes. So if we have a firewall and you have 100 of a session, which is a true for mid-range firewall, we receive a huge amount of memory that it needs. And this, I think, is the main reason why they decided to ignore compressed traffic. So our solution was to understand that most of the time you don't need a 30 kilobyte in the uncompressed form. You can decompress it. The compression is some light version of the compressed form of the traffic. It's not the same uncompressed traffic, but with some adjustment. We receive space reduction of factor of 5. The mechanism takes time, but since we know how to accelerate DPI on compressed traffic, if we combine the two works, we will see that we improve the space by 80% and the time by 40%. Not by factor of 2 or 3, but still huge. And this is from this paper. Okay. Now I want to talk about the last challenge. I will only introduce it. And the question is how we secure the deep packet inspection. So, as I told you, in many places, the firewall runs some kind of deep packet inspection. And then the attacker, knowing the mechanism of deep packet inspection, can easily craft a hard packet to process. Then the firewall will stop working, and the attacker can sneak to the network. This is not only theoretical. Similar approach was done in the Sony attack a few years ago. They started by DDoS on security elements. I don't know if the DPI or something else. And then they exposed the network, and then the attacker stole customer information. Okay, so why it's so easy to attack the DPI engine? And this is because the environment of the deep packet inspection. You have the CPU, you have the main memory, but a major factor of the performance is the cache. Okay? The data structure is usually huge. Okay? This is a kind of DFA or something like that. But in security tools, especially, only the head of the data structure is used. This is because in security tools, the pattern are pattern of malicious activity. And usually, we don't suffer from malicious activity, so usually there is no match. So usually you have a very high locality. Okay? So what the attacker can do is reduce the locality, getting stuff out of the cache, so the DPI will be much, much slower, and it stop scanning part of the traffic. We implemented such attack on the open source Snort. We send heavy packets that's hard to the deep packet inspection, and so how the throughput and goodput reduced dramatically. And a paper from a few years ago, we present a solution that uses multi-core or multi-VMs environment for solving this kind of attack. So what is the, I want to sum up until now. The current status, and I hope I convince you, is that DPI is a complicated task, and that you can gain from complex algorithm. And yet, every company designs its own DPI engine. Okay? And this brings me to the last point, the opportunity DPI in SDN and NFV environment. So what is the SDN and NFV, and how it influences middle boxes and deep packet inspection? So software-defined network give you the ability to control the forwarding easily, and network function virtualization means that you will move from hardware middle box to software middle box. And the fact that there is SDN influences a lot of how you implement service chain. Okay? Until now, I talked that the traffic goes through one middle box. But usually in a network, the traffic goes through several middle boxes. It's called service chain. And in classical routing, usually you should have to put the middle box on the route between the source and destination, because it was hard to control the forwarding of the packet. Now with SDN, because you have the ability to control the forwarding of the packet, you can put the middle box in any point in the network, even in the steering point, and then you can forward the traffic with very complex route from the firewall to the IDS, and then back to here to the proxy, and then back to here, and even loop, and you can configure it that he will succeed to implement this route. Network function virtualization means that the telco company decided that it's enough that they have such many different boxes for many vendors, and they want to move to a software that will be in their private cloud. So NFV, hardware middle box, moving to software middle box, and the basic idea is that the disadvantage of hardware middle box is that it's not flexible, it's expensive, it's hard to manage because you have many vendors, it's not multi-tenant, it's difficult to add new features, and it's constraining the innovation because it's higher entry barrier. You want to build a new middle box, you need to build a new device. So moving to the software middle box will solve all this stuff, but there is a drawback that might be performance penalty, because you run on commodity servers, you run VMs, and you don't have hardware accelerator. By the way, there are hardware accelerator to deep packet inspection. There is the solution of Intel, and some of the middle boxes use hardware to accelerate deep packet inspection. So what we suggest is a new middle box architecture that improves performance and innovation using NFV and SDN. So benefit from the two worlds. Okay, so let's understand the basic idea. If you look on the service chain, you will see that each packet is scanned multiple times in deep packet inspection, because most of the middle box use deep packet inspection, which means there is a waste of computation resources. And each middle box implements its own DPI engine, which means higher middle box costs and reduced features. So the idea is to take the DPI engine and suggest it as a service. Okay? This means that the middle boxes will tell the DPI instance the set of the pattern. The DPI will work on the combined set of the pattern, will see which patterns will match, and then will send the result on the packet to the relevant middle boxes. So what is the benefit? The benefit is now DPI is a service. It means that we increase the innovation because you have lower entry barriers, because you don't need to implement the deep packet inspection. You have reduced cost. You don't need to build the deep packet inspection. You improve performance because you scan each packet once and not again and again in every middle box. You have rich DPI functionality because we invest in one point in the network and build a very clever DPI. And we enhance the data plan. It means that even switches and routers can enjoy from the fact that there is a DPI as a service. So let's look how it will be in the network. Here you have some service chain. And now we take the DPI. And then the traffic will go to the DPI, and from then to all of the middle box. And this is the mod device service chain. If we look on the architecture, we see that we have new element. We need DPI controller. The DPI controller will receive the set of the pattern from the relevant middle box. We can have also several DPI instances. So in this case, we'll have also the work to divide the pattern to the different set of the DPI instance. A little bit about the outline of the solution. We have the DPI controller. We need also mechanism for passing result from the DPI to the middle box. Don't worry, there is such. It's called network service header. It's internet graph and Cisco is implements stuff like that. It's for exactly sending information from one middle box to another middle box in the service chain. And also we need scalable DPI algorithm. Because I promise you that it will improve performance, it can improve performance only if the time requirement is sublinear with the number of patterns. Since the DPI instance takes several pattern sets and combine them together, you can enjoy from this only if the algorithm is sublinear with the number of patterns. And in reality, in many implementations, this is the case. Okay, and this is the work for previous codecs. The industry seems to go to solutions that are suggested as a service. For example, there is a company, Cosmos, which suggests application-aware classification as a service. Cosmos suggests an NFV service that classifies traffic to the type. It adds a tag that classifies if the traffic is Skype, voice over IP, Instant Manager, or FTP. Okay, so we see similar stuff in the industry. So a little bit conclusion about deep packet inspection. I hope I convince you that it's evolving area and that the fact that SDN and NFV will change the field of middleworks, and I think among other the DPI area. The exact details how it will be, time will tell. Question?
Just repeat the questions.
Okay. If I will have a question, yes.
So you talk about compression. What do you do when it's encrypted, or you just give up?
Yes, it's a good question. So, yeah. What should I do with encrypted traffic? So, in many cases, security tools knows the key. So they open, it takes time. And maybe you can accelerate stuff like that if you know there is repetition or stuff like that, but we didn't look into it. If you don't have the key, by definition, you cannot do anything which is a deep packet inspection. And there, security tools try to understand stuff from the size of the packet and stuff like that. Because shortly, you are in trouble if it's encrypted. Yes?
Well, since you have one service that performs this deep packet inspection, so what happens if a hacker manages to break into this service? So none of the middle boxes would receive this the service that they are expecting. So you have like one single point of failure now instead of having multiple.
Yes. So the question was that because I suggested DPI as a service, I have one single point of a failure. If the hacker will attack the instance of deep packet inspection, all the middleware will stop working. Yes, I think it's a good point.
Is there any work done on this? How do you protect the service, or is it not?
So what I think that if it's true that you have a single point of failure, but you have also a single point that you can protect and harden the algorithm so it wouldn't be vulnerable to attacks. In today's network, everybody design its own deep packet inspection, and most of deep packet inspection, in reality, when we check, you can perform against them DDoS. And it makes sense because if you need to design from start the deep packet inspection, you don't have time to think about all the aspects of DPI and secure them. So it's a question, what is better?
But the attacker had access to the controller at all? I think...
To which controller?
To the controller of the DPI.
The question if the attacker can have
Also the controller of the SDN?
this is what I want to answer. If the attacker can have break to the controller of the deep packet inspection, it's the same if the attacker can attack the controller of SDN, but the controller of SDN, it's much worse problem because if you attack the controller, you wouldn't have no routing, no forwarding, and all the network will be attacked. So you should protect the DPI controller the same way you protect the SDN controller.
There's a question if you can use DPI is a network partial initialization because you have to move practically every packet. I mean, the way I see NFV is that, you know, there's some control packet you need to move maybe longer routes and have some longer delay, but here you actually want to take all the traffic. So is it doable at all?
I think that the question was, okay, I need to know how to repeat it. Maybe you will say it loud. The question was that in NFV, you think that every packet should be forwarded to deep packet inspection, and you think it will make a high delay and to be problematic, and you don't think that everything will be on the NFV. This is the question. So I think that it shouldn't be every packet, just packets that need a deep packet inspection. So you can have service chain that wouldn't go through the deep packet as a service. And also the deep packet inspection, the instance, can be also in hardware. Okay? If you need to accelerate it, the same mechanism will work if you implement the deep packet inspection as a hardware. So the NFV will be the middle boxes, not in this case, not the deep packet inspection instance if you need a very fast solution, but only the middle boxes. And also, I think nobody will know now what will be in NFV and what will be in devices. Time will tell. It's a very evolving area now.
More questions?